necessary to sample isokinetically to ensure that a representative sample of the particulate emission is obtained. Second, it is achieved through maintaining desired flow rate through nozzle and sampling at appropriate multiple points. Sometimes with limited access to sampling lines, sampling points and poor positioning of sampling plane, one is forced to assume certain measurement. Now I show you the earlier slides. Suppose it is not meeting the criteria of 80, then in order to meet the requirement, you need to increase the number of points. The whole purpose is that we should be able to do the sampling isokinetically. Now what is happening in isokinetic conditions? Suppose your suction from the nozzle is the same at the rate at which it is going out. It means at the tip of the nozzle, once you do the sampling, do that particular collection, then you will be able to get the correct type of dust particles you are looking for. But suppose the suction rate is higher or suction rate is lower, then you will not be able to get the right concentration. So you have to be very careful that whenever we are doing the monitoring or doing the particular sampling, isokinetic conditions have to be maintained. Do we need these isokinetic conditions for gaseous samplings also, for gaseous Cems? No. Right. So this is basically an exercise. We are doing it for PM, particulate matter. Now the requirement says suppose the diameter of the stack is up to 0.3. Now in that particular case you can go for the traverse points which are 4 in numbers. And plane 1 basically means only one photon will be sufficient in the scenario where the diameter, this is the inside diameter, see. This is not the outside diameter. This is the stack diameter from inside. So if it is of the order of 0.3, then you can go for 4 number of traverse points. If you go from ID is 2.4 up to 5, then you need to collect the sample at 32 points. So in order to do the sampling at 32 points, you need to have 2 planes. It means you need to have at least 4 portholes, and then you can carry out the monitorings from 16 points from each particular porthole. If it is more than 5 meters, which is normally most of the case in thermal power plants, the diameter is always more than 5 meters. You need to carry out the sample at 52 traverse points, and each divided into 2 planes and 26 from each particular side you need to collect the sample. The idea is that we need to collect the sample at these particular points so that the sample what you are taking is the representative sample. Because once you do the sampling, you can derive how much is the dust concentration, and that dust concentration need to be fed into the Cems. And Cems is somewhere all the times more or less stationary. It will not move. So you have to be very careful that whenever the value of Cems is being entered, this particular whatever is the dust concentration, all these steps need to be followed.
Sir, this is practically this sir, the last one. Practically.
Do you see any problem?
I suppose the duty manufacturer boards needs to be boards.
That's right. See, that's what I said. All the existing industries, probably they may not have the provisions, but the requirement says that you need to have it. In the new particular installations, wherever it is happening now, people are taking care to provide all these necessary requirements, which probably was not there. Sometimes that particular thing is not possible. So there is always a scope where you need to assume, you need to come very close to the particular real values, either by increasing the probe length. I do remember we have manufactured few pitot tubes for L&T. They were doing it for a specific purpose. They asked us to draw a particular pitot tube which is 6 meters in length. So transportation was a big issue, but then they could able to perform that test using so many lengthy pitot tubes also. So practically, see, you have to keep it in mind that the requirement is something which you have to know that these are the requirements. Then comes the second part, how to accomplish, how to see that you are going very close to that. I'm not saying it is always practically possible, but then you need to put your heads to and see how you probably can carry out the monitoring. Because in the law of court, this particular thing will not be accepted that practically it is not possible. They will not listen to you. So you should know, if it is not, then how you are managing it, how you are doing it. These are the basic requirements what they have mentioned. Same. See, two planes in the earlier slides you have mentioned. This one. So this is one plane. If you insert the probe from one side, you go into the other side. This is one, and this becomes the second plane. This is actually a vertical photograph. If you see horizontal, one plane and the one from the other right hand. For rectangular ducts, Mr. Sen has also showed you that formula, that 2LH by LH. Sometimes it is not possible to do the monitoring on the stack. Sometimes it is that the monitoring need to be done on the particular ducts. So ducts are mostly in rectangular in nature. So you need to convert the particular size of that particular duct into equivalent diameter using this particular formula. Fit into that formula and then see how many number of traverse points need to be covered. Now in order to know what are the distances of various traverse points from the wall of the chimney, a chart has been cleared, it has been given by CPCB regulation part 3. How many of you have gone through that CPCB regulation part 3? See, this is very surprising. See, all of you wants to use Cems, but the basic guidelines which is available in that Cems, that CPCB regulation part 3, most of you have not gone through it. See, it is easily available at the site, and I will request all of you to go through that particular CPCB document before you actually go for Cems. Because see, if the basics are not very clear, probably whatever Cems that is being installed at your premises, you will not be able to do full justice with it. So you should know the requirements, you should know how it is being carried out, what are the process, what are the things. All of you should go through that document and then only should come forward where you can ensure that whatever data is being now given by Cems is as per your requirements and is as per actual source. So this chart is available where they say if the number of points is, say for example, that 16 what they mentioned. So in that 16 column if you come down, so these are the distances for that 16 points from that particular stack wall. So you have to be careful. These are the distance from the inside. For example, this is the place 1, 2, 3. This way you have to select 16 points. And the points which you need to keep it in mind is the particular wall thickness. Because see, there was in Bhubaneswar where we had carried out the monitoring, the wall thickness was half a meter. And then there is a particular joint where the particular flange joint is of the order of about 10 inches. So if you see, the probe length has to be considered where these particular points very relevant. If suppose half a meter plus another 1 feet 12 inches, you see 60 centimeter of the space has been taken away by the wall only. So you are not actually going inside the stack to collect the sample. Now this is just to make you about your query also, what about the plane. So a core circular diameter is divided into equal parts. This is the one which is being done for 16 zones, and each zone then you need to collect the sample at these particular points. The idea is that the whole particular diameter is divided into equal areas, and then you are doing the sample from that particular plane from the center of that particular area. So idea of that 16 is that the whole diameter has been divided into equal parts, and then you are doing the sample from the particular center of that particular area. See, it is an imaginary thing. It is not something which probably is drawn into that. But the moment you make that particular chart, that particular sampling, you need to go step by step where you need to know that where I need to collect the sample from. You need to put it on a paper, you need to draw a chart, and then you see at what distance I need to place my probe so that I am able to collect the sample in the proper. Is that clear up to this point? Same way for the rectangular duct also. It is a rectangular duct, so you need to at least have 1, 2, 3, another 1, 2, 3, 4. basically meeting these particular requirements. Because in most of the duct, what we have seen, that there is only one porthole. Is it true? Yes. So the idea of doing this particular exercise is, we should know that you should be collecting the sample from various planes. Then only you can get the representative sample. Same way you need to put it from the top also sometimes. So the idea is that you are able to cover up the whole of duct. Now just to take you, how many of you have used a stack monitoring kit? 3, 4, 5, 7, 8. Okay. Now just to see that most of you have not used it, just to tell you how that particular system is working. Because do you find it difficult? The people who have already used the stack monitoring kits? Is it? People often complain that it becomes a very difficult exercise. But friends, see, it's a difficult till you don't do it. I think the moment you know the basics, the moment you start using it, step by step, and I'm very sure that probably by the end of tomorrow, I think most of you should be able to use, should be able to do the calculations, and at least will have a fair amount of idea how this stack monitoring exercise has to be carried out. Now just to make the thing simpler, what we have done, we have divided the whole stack into 3 different parts. The first one is temperature, the second is velocity, and the third is the sampling front. So I'll be taking by one. See, this is the probe with the red mark. This is the thermocouple probe in order to know how much is the temperature inside the stack. See, the difference between the ambient air quality station, monitoring station, and the stack monitoring is, the first thing is, we need to collect the sample at high temperatures. In ambient air, what were you doing? You were just putting the instrument in the ambient air and then collecting it. No. In this particular case, since you will be doing the sampling from the stack, the temperature in the stack is much higher. So you basically need to have a method by way of which you can know how much is the temperature of the flue gas. So we have a parameter, a thermocouple which is attached to a parameter, and then you get the values of temperature. Then comes the next step. We have a S-type pitot tube. A pitot tube is used in order to know how much is the differential pressure inside the stack. So we use a pitot tube which is connected to 2 ends of a manometer. This is a digital manometer. In earlier cases, we were using red oil as in the manometer, and we were calculating how much is the differential pressure on a manometer scale. But now with the change in technology, we have digital readout manometer which can directly give you how much is differential pressure. So once you know how much is the temperature, then you know how much is the differential pressure. You need to then calculate the velocity. In the next few slides, I'll be showing you how those particular calculations is done. But in order to show you pictorially how the things are being done, the third part comes, this nozzle is there. See, this nozzle and there is a filter holder. This filter holder contains a thimble. Thimble is the place, it's a filter only, which will going to collect all the dust particles which are going in the stack. So we need to collect those particular dust particles in that thimble. It is connected to 2 rotometers, one for the particulate and for the gases. And we need to, actually the gases are at very high temperature. So you need to basically have an arrangement where you are able to take care of, one, you have to cool down the temperature. Second, we need to, for the gaseous part also, for the gases monitoring, we need to absorb it in a place where you are able to then have a better conditioning of that particular gases. So this is the place where we need to ultimately be connected. Sorry. This is connected to the vacuum pump. So all necessary suction is being provided from this place. And we have, this is a full schematic of that monitoring system, which we will be going to use it tomorrow. Just to make the thing simpler, everything has been put in a way so that you can understand the various steps which are involved into manual stack monitoring. Now at the back end is, what is there is, we have a sampling tray which is an ice tray. Why is it called ice tray? Because we are supposed to put ice in this particular tray. Why ice? Anybody? To cool down the particular hot stack gases. Any other reason for this? Any other reason? See, the other reason is that whatever gases which are being absorbed, for better absorption efficiency, if it is high temperatures, then probably at the end of sampling you probably may not be left with any chemical reagent in these glass bottles. So for better absorption efficiency, you need to pack ice all around the glass enclosures. And the idea is, basically we are carrying out the monitoring of both particulate as well as the gases together with the existing stack monitoring system. Now I come one by one on the various aspects. I think most of you probably can, the calculation part, will be doing it tomorrow. But what is more important about the various points which probably I need to discuss with all of you, that whenever we are attempting to do this particular monitoring, there are few mistakes which are being carried out very often, and I probably feel that these things we should keep it in mind while doing the monitoring. The temperature to be noted after it gets stabilized. Whenever somebody goes for the monitoring, probably is in a hurry, will put the probe, will not wait for the temperature to settle down. Whatever the reading comes, he will immediately takes it. That is not the right way. You need to wait till the temperature gets stabilized and then note down the correct temperature. Thermocouple should not touch stack walls. Stack wall is this much. Your thermocouple is touching the wall of the stack. You are not actually getting the temperature of the stack gas. What you are getting is temperature of the walls. So that is not the right procedure. Temperature can be taken at one point. For the traverse points we have said, you need to do the monitoring at 16 points. Temperature more or less remains constant in a plane. So you can probably carry out manage the show with one particular point also. Thermocouple and pyrometer should be calibrated and must be of the same type. How many different types of thermocouple? Anybody? I think most of you are from the field area. We use type K. Any other types which is there in the market? R type, J, PT. So various types of combinations are available. So keep it in mind that whenever you are using a system, both of them should be calibrated and must be of the same type. Invariably, sometimes many people have more number of instruments. They are not very particular about which probe, which particular thermocouple. So try to use both the things of the same polarity. Type K, your thermocouple and the pyrometer should be of the same type. Provision should be there to measure temperature of flue gas at metering point also. So whenever you are doing the measurements of flow, you should have the provision to measure the temperature also. Why is it required? For stack calculation? Where? For the correction. See, what are the values which are being reported for thermal plants? How much are the limits? How much is the value today? 50 units, 50 milligrams per normal meter cube. What about the ambient air? 100 microgram per meter. So what is the difference in the units? Normal, N. See, this N becomes very important, and that's why whenever we are doing the stack monitoring, you need to report the data in milligrams per normal meter cube. And this N, the requirement is whatever the readings you are taking has to be brought down where you need to do the correction both for temperature as well as pressure. If this correction is applied, then only you can report the values. But you never say, for example, in a cement plant in Bhopal, whenever they are reporting the data, they'll always say so much, so milligrams per nm cube. They don't specify the place. Where for the ambient air, the requirement is you need to specify where exactly that dust concentration is. And that's why one particular 50 is probably applicable for throughout India. Whether you do the monitoring in Shimla or you do the monitoring in Chennai, the values, the units, you have to bring it down to normal meter cube, and then you can compare the data. And that's why whenever the data is being transferred to the PCB portal, they are not very particular from where it is coming from, till it is being reported in NMQ. So this point you have to keep it in mind. Now comes the second part, which is the measurement of velocity. These are calculations which probably all of you will be doing it tomorrow. I come to the main points of this one. The orientation of the pitot tube. See, when you are doing the monitoring inside the chimney for calculating of the differential pressure, the orientation of pitot tube becomes very important. You need to put it in a proper plane, and wherever it is going, flow is going up, so your pitot tube should be in a way where it should be facing that particular stream. Suppose it is a horizontal stream, then you need to put the pitot tube in a way that if it is flow coming from that side, this should be the positive end. Leakage check. What will happen suppose there is a leakage? Anybody? पानी की पाइपलाइन है उसमें बहुत लीकेज है क्या होगा? What will happen? Probably nothing will come. So you should ensure that whatever system you are using, it should be leak proof. These are very basic things, but then somebody needs to go and do the monitoring, need to ensure at least there should not be any leakage. Tip of the pitot tube to be protected from bending and deposits, because in the calibration of the pitot tube, it is the tip only which plays a very important role in order to know how much is the pitot cost. Cleaning of pitot tube from inside, once you are using it on a stack, naturally it's quite likely to get dirty. So after each monitoring, clean it from inside with an organic solvent and then make it ready for the next monitoring. The number of sampling points to be decided on the basis of diameter of the stack and location of the portal for representative sample. I shown you two earlier slides. So number of sampling points, suppose the diameter is more than 5 meters. So how many travel points you have to take? How many? For more than 5 meter stack, how many points? 52. Pack of the cards. Okay, 52 points is something you have to keep it in mind. So once you know this, I'm coming, see that particular chart, everything is being related to how we need to carry out the monitoring. So this is the point, the number of sampling point to be decided on the basis of diameter of the stack. And the location of portal. For example, it is not at 8D, it is at 6D. Then what will happen to the number of traverse points? Multiplied by 1.5. So basically that 52, another into 1.5, you need to add 26, it becomes 78. So basically you need to then collect the sample at 78 traverse points. So all these particular things becomes very relevant once you are going for the calculation. Is it clear or? Sorry, one point. The calibration of pitot tubes is absolutely essential. See, no pitot tube is valid till a valid calibration constant is being given. Anybody using a pitot tube, and you know how much is the constant which normally they get? Anybody who is using a pitot tube? More than 0.85. So on an average, a S-type pitot tube is carrying a pitot constant of the order of 0.85. And each pitot tube, whenever it is supplied to you, do make sure you need to ask for the pitot constant. Any pitot tube without a pitot constant has no meaning. So that you have to keep it in mind. There are other types of pitot tubes also available like L-type pitot tube, which is having a pitot constant of the order of, anybody? For L-type pitot tubes, it is always 1. That is also taken as the reference. But then L-type pitot tube is not recommended for stack monitoring. For stack monitoring, we need to do measurements by S-type pitot tube only because of the large portal, which is large area which is available for doing the velocity calculation, measurement parts. Now we have done the temperature viscosity. Then the third part comes how to do the particular sampling from. This is once again the formula. I'm probably very sure tomorrow we'll be doing it. I'll come to these particular points where I mentioned in order to do the sampling isokinetically, what are the various points which need to be now taken care of? The first one is appropriate nozzle on the basis of capacity of rotometer. Now these calculations, once you put the particular parameters, you will be actually calculating the flow rate. Then we need to select an appropriate nozzle. So this will depend upon the capacity of the rotometer. In the rotometers, normally what is being supplied is 30 liters per minute. So you need to select a particular nozzle where the flow rate is of the order of less than 30, so that you are able to do the sampling at desired flow rate. Second, appropriate thimble on the basis of temperature. How many different types of thimbles have you seen? Anybody? Cellulose, glass fiber, anything else? Cellulose can withstand temperature up to 150 degrees centigrade, we normally say up to 120. Glass microfiber thimble can withstand temperature up to 500 degrees centigrade. Now suppose the temperature is still more, say 700. What will you do? Quartz. Quartz thimble are available, silica thimbles are available, which can still withstand temperature beyond 700 hours. There are sometimes ceramic thimbles also available, which are reusable, but probably we do not have it in India. But sometimes we have seen that ceramic thimbles are also available, which can withstand temperatures of the order of 1000 plus degrees also. So, depending upon how much is the temperature of the stack, we need to select the thimble. The third is the time period for which the sample has to be taken, for which the criteria says you need to collect 2 to 3 grams of dust, or you need to pass 1000 liters of gas. What it is? Suppose the flow rate comes 25 liters per minute. So in order to meet this particular requirement, for how much minutes I need to collect the sample? 40 minutes. So 25 into 40, that makes 1000. Suppose the dust concentration is high. Can you do the monitoring for 40 minutes? Yes or no? No. Because if you do the monitoring for 40 minutes, your thimble are likely to get choked much faster and probably will not be able to collect the sample. So what you need to do, the other criteria by slide back calculation to see if you are able to collect about 2 to 3 grams of dust, which is basically required to do the effective measurements on a balance, then you can reduce your sampling period to 5 minutes or 10 minutes, or depending upon the requirement. Is it clear? Because see, these are the 3 points which you need to take care: appropriate nozzle, appropriate thimble, and the time period of sampling which is required. The fourth one is the important part, the flow rate. For the PM and the gas stream, whatever is there, so we can do the provisions of simultaneous monitoring also, so that both particulate as well as gaseous monitoring is being done together. And there you need to ensure that whatever flow rate which has been calculated, you are able to effectively put into 2 streams, one for the particulate, the other one for the gases, so that the particles which are coming inside the thimble is meeting the requirements of the isokinetic flow rate. Now at what rate? Yes sir. That's very good. That pressure correction is very much required, but pressure correction you cannot get till you do the sampling. So what happens is, while doing the calculations, we will do the calculations assuming some of the pressure in the beginning, but while doing the monitoring, we will be actually measuring the temperature and the pressure also at the metering point in order to provide the necessary correction at the end. Whatever isokinetic flow rate, necessary correction need to be applied at the end. pressure, and see that is at the end of the sample.
So for LPM, I think it may be increased. If the pressure correction and temperature is not done, I think the isokinetic sampling is known.
No. See, what you are saying is absolutely correct, but the thing you have to keep it in mind is that whenever we are doing the things manually, we are maintaining the same flow rate, trying to increase that pressure. So what happens is we are changing the flows almost continuously just to see and ensure that you are doing the sampling at say 25 liters per minute all the time. If it is falling, then you need to increase that particular sampling. So this is how you will be able to achieve. You see, you have to actually go near to that particular value. Otherwise, there is no end. So what we do is, if the with the loading of the thimble, the flow comes down. You increase the flow so that flow rate is still maintained at the same what is required, and then do the particular correction at that. What you are saying is absolutely correct. I don't deny, but this is the way the process has to be carried out. Important once again, the leakage should be zero. Suppose regulators are there, what will happen if there is a leakage? You will get more concentration or less? Less. So regulators will not allow you to take the monitoring, do the monitoring with a system which is having leakages in the system. Sufficient ice should be kept in ice tray. I have already explained you that why ice is required. You need to see and ensure that sufficient ice is put in the ice tray. One, in order to bring down the temperature of stacked flue gases. Second, in order to have a better absorption efficiency for the gases polluted. The third, orientation of nozzle and handle. Now, why orientation is important? Anybody? Yes. Suppose the stack flow is from bottom to top, and if your nozzle from where the gases is being collected is this way, then it is all right. But suppose you have put it this way, what will happen? No collection. So what happens is, in our system, we have incorporated one handle also, because most of the times you are not actually going up the stack. You are there on the ground floor, you are not going up the stack, so you do not know whether that probe has been inserted properly inside the stack. So a handle has been provided where you have to align the nozzle and the handle. Handle is kept outside, and then you know at what particular angle that particular nozzle is placed. So whenever you are doing the sampling, just see and ensure that the orientation of nozzle is proper.
So any criteria for the design of the nozzle?
Yes. See that area, once we do the calculations tomorrow, there are 3-4 different types of nozzles with various internal diameters, just in order to calculate how much is equivalent to the isokinetic flow rate. So these nozzles with different internal diameters are available, and then you need to use that in order to calculate the total amount of isokinetic flow rate. How do the calculations? We'll be doing it tomorrow at site, where you will be actually carrying out. Then you can understand in a better way that why 3 nozzles, why 4 nozzles are being provided with different internal diameters. That is just to see and ensure, because isokinetic flow rate is something which is more or less stable. But since you need to carry out the sample isokinetically, at the tip of the nozzle where you need to then fix up the velocity. So that nozzle is a variable thing which is there with you. There, by changing it, then you can set the flow and then collect the sample. The sampling at various traverse points. As I said, 52 traverse points. So how will you do that particular monitoring? Thimble sabba nikalenge, or do we take out in one shot? So 52 means instead of 40 minutes, we'll do the sampling for 52 minutes. In one plane there are 26 points. So every point we'll do the sampling for 1 minute. We'll move the probe at the second spot, once again collect the sample for another 1 minute, and then keep on doing it. So these particular traverse points, you need to divide the whole time period accordingly. It's not that you need to do the sampling for 40 minutes at one point, no. We need to collect the sample from all traverse points, and then you need to collect the sample on equal time interval also. that is required. The last one, pressure drop and the temperature at metering point to be recorded. This is once again for applying that pressure and temperature correction, which need to be applied in the formula. And what is that formula? This is the place where in order to know how much is the dust concentration, you need to apply this particular correction for temperature and the pressure so that you can report your data now in mg per NM. Now why this whole exercise has been done to find out this dust concentration. Now this dust concentration, what is the requirement now? इसे क्या करेंगे? Why we did this particular exercise? See, PM Cems का जो calibration है, वो इस value से. Okay. So what is required to be done is, whenever you are doing the manual stack monitoring, you need to install, you need to run your Cems also simultaneously. So the idea of getting this particular thing is, the moment you know how much is the dust concentration, the dust concentration factor need to be then put into that Cems, and then you can start getting the values which probably you have calculated and measured. Is it clear? Why we are doing this whole exercise? Basically to know what is that dust factor. That dust factor is something which you need to then put into the Cems. कितने लोगों ने किया actually monitoring? या सिर्फ Cems लगा के चल दिया ऐसे? Did it? Only 2, 3, 4, 5, 6, 7. What are the other people have done? Have they really done that particular exercise or no? No. Okay. So I think that is very surprising. See, that manual monitoring is a must. And I'll show you in the next few slides also that even from the regulating point of view also, from the regulator point of view, if you are not doing this manual monitoring, probably your data will not be accepted. So, just to show you, many of you may not have done this sampling exercise. I'll show you some places how that particular monitoring is being carried out. This is a very good place where you have a good platform. Many people, they have put a table also and then are able to collect the sample from the start. Now this is also a place where the sampling is being carried out. किसके यहाँ पे इस तरह से होता है? Many stacks? No. Okay. Many times people are doing that particular stack monitoring in this fashion also. This may be alright from the measurement point of view, but from the Cems point of view, this is not at all an ideal situation. You need to avoid this. This is a place where we have a demonstration. We have a very good arrangement where you can go up by a lift, and they have enough space where all this particular monitoring is being carried out. This is once again a portal which probably does not have a very good platform, but then at least some arrangement is there where you can put your instrument, you can install Cems also, and then do the monitoring. This is once again another photograph. This is a place where they have installed a Cems, and you have the provision for doing the manual monitoring also. This is once again a place where a Cems has been installed, and then you need to have a place where you can carry out the manual monitoring also. Now these are the few requirements which probably in order to do this exercise, probably with our past experience, I feel that whenever we are carrying out the monitoring, it is very much required both for regulators as well as for industry, as well as for consultants also, that whenever they are carrying out the particular monitoring, they have to see and ensure that these particular things are taken care of so that you are able to effectively do the justice with that monitoring. The first one, site visit prior to monitoring in order to understand physical and logistical situation on site. Now this is something which probably sitting in an AC room, you cannot know what is the situation actually on the stack. So site visit prior to whenever you are carrying out a monitoring exercise is very much essential to know what are the place, how particular thing, how will you move your instruments, how particular Cems will be installed. So a site visit is very much required. The dimensions of stack and details of monitoring facilities are available. Now why dimensions of stack is very important? See, for example, in Bhubaneswar, the diameter there is of the order of 15 meters. And my sampling probe is only 1 meter. So suppose I take a sample from that 1 meter probe with a wall thickness of half a meter, with another flange joint of the order of about 12 inches, probably I'm not entering the stack at all. Whenever you're doing the mounting, suppose the edge of the wall, my probe will come only up to this point. It is actually should be able to cover up the whole stack. So the whole plane need to be covered. So I should know what is the diameter of the stack. And then accordingly, I need to select appropriate probes, appropriate length of thermocouple pitot tubes, so that I am able to do the representative sampling at all traverse points. So if you don't know the diameter, probably you will not be able to achieve that particular objective. Access to stack and adequate work area at the sampling plane. I'll just show you with the photographs. If there is no space, probably you cannot be able to install either Cems, you will not be able to do the monitoring properly also. Availability of the required utilities like electrical, lighting, water, ice. If you're going on almost at the height of say 80 meters, everything has been taken care of and there is no electric supply. It has happened many of times. It happened. So this is a signal basically to see and ensure that all the things need to be adhered to. So everybody, I think most of you might not have sleep, and probably you have to wake up and see. Required utilities like electrical, lighting, water also. Sometimes you have reached the height and there is no water with you, there is no ice. So probably it becomes very difficult to climb 80 meters, then come down to take water and then once again go. So these are the few things which you have to prepare yourself. Expected velocity profile, temperature, moisture in the stack gas. Now this is something probably may not be available with you, but most of the people who are performing this particular test in the process, this data is available with the control room. So don't see that you need to collect it, you need to collect the data from control room also, from the people in the process, to basically know how much is the particular profile of the temperature, why temperature is required. Anybody? Why do we need temperature beforehand? Is it required for the selection of appropriate? What will be thimble? So if you know the temperature, you will be preparing yourself to take that thimble only. Okay? So idea is that this particular profile should be known, should be made available to you. Restrictions on using equipment, like for example safe areas. As in the morning Mr. Seen has also mentioned, and Mr. Ronald, suppose it is something where fire hazard is there. So you need to install an instrument which is ATEX approved. So all those particular things, whenever you are doing the monitoring, keep it in mind that the area where you need to carry out the monitoring, is it safe to use that instrument or not? Appropriate measurement equipment like length of the pitot tube, sampling probe, suitable thimble, etc. for the application. So once you have the above data, you can very well then select appropriate particular hardware with you. Competent manpower with knowledge of process and details of monitoring method to be engaged. Now, competent manpower with knowledge of process. See, many times what we have seen that the people who are actually doing the monitoring, they actually have not done that particular, does not know what are the back end of that particular calculation, what is required to be done. So the idea of making these things available with you is that whenever the person who is actually going for the monitoring should be able to take care of these requirements, should know actually why I am doing it, what are the areas which probably it is not done properly, then probably you will not be able to do full justice. So try to see and ensure that you are able to train your manpower also. And writing material is being circulated. Emission regulation part 3, which I have requested all of you to go through that document. I am very sure most of you may not have gone through it. Go through it. Probably there are many areas which you probably feel after reading it that most of the queries have been solved right then and there itself. Phobia of heights should not be there. कितने लोगों को आपको phobia है the heights? किसी को नहीं है? Only one. So that's really good. But can you climb up to 80 meters? Yes? Okay, so I think Sanjeev ji, most of the people are ready to climb 80 meters in a monkey ladder. Okay, all right. Okay. Not on monkey ladders, only through lifts. So be sure that the people who are actually doing the monitorings, they are going up the stack, should not have phobia of heights. See, there is nothing to basically make the things known at the beginning itself. Otherwise, there are many circumstances where people have gone and midway they probably start fearing. They have to be brought down. So see that this particular phobia, if it is there, never go up. This is for the safety of all of you. Proper dress, safety shoes, belt, helmet, etc. should be available. Sanjeev ji has also, I think, for the tomorrow, he has removed this particular criteria. But whenever you are going to a site, this is something which is very much required. Don't feel that you can just go there and do the monitorings with the plain clothes. No. You should prepare yourself for any eventuality and take care of the proper dress, safety shoes, belt, helmets, etc. should be available there. Now the regulatory requirements. Many of you have said that only providing the data will it be sufficient, or what are the criteria? So the document by CPCB, they have stated most of the things and try to follow the particular requirement which they have mentioned it very properly. The continuous particulate matter monitoring system Cems shall be calibrated at different operational loads against isokinetic sampling method, triplicate samples at each load. Means whatever is the working condition, you need to collect 3 samples, at 0 also, and some of the other points, at least 3 various loads need to be covered, and at 3 loads you need to collect the sample 3 times. So basically 3 into 3 becomes 9 particular points are required to basically make a graph and then put that particular value in Cems. What is after that? At the time of installation and thereafter, every 6 months of its operation. So this is the requirement of regulators, that whenever you are installing a particular Cems, then these are the 2 requirements which need to be taken care of. The second, the results from the particulate matter monitoring system shall be compared on fortnightly basis. Every 15 days. कितने लोग आप में से करते हैं 15 दिन में मॉनिटरिंग एक्सरसाइज रिपीट करते हैं? Anybody? Okay, that's really good. 7, 8. So every 15 days you need to have that manual monitoring system. आपके पास में है. You need to go there and do this particular test. It's not you need to do only after 6 months. No. Every 15 days you have to basically do this particular exercise at your end. They have specified the time and date also. They have said every second Friday of the fortnight at fixed time. It's a replicate sample starting 10 a.m. with standard isokinetic sampling method. Now these are the requirements which has been specified by the regulators, by the PCB state boards, and all of you, after installing Cems, don't stop there. You have to basically see and ensure that these particular requirements has to be taken care of. Don't depend upon only the consultants who will come once in a while, do the monitoring and submit a report. No. The requirement says you need to have your own infrastructure, you need to make this particular exercise yourself, because every 15 days, you cannot call them and do this particular thing. In case, now what happens the next step? In case deviation of the comparison values of 2 consecutive monitoring is more than 10%, the system shall be recalibrated at variable load against isokinetic sampling method. So if the variation is of the order of more than 10%, then you need to once again calibrate your system. Yes. No adjustments of calibration dust factor, CDF, what they have said. What is CDF? Calibration dust factor. What we have done at the dust concentration, they say it is a CDF, calibration dust factor, which need to be put into the Cems, and then it will start giving you the values. And no adjustment is allowed unless full scale calibration is performed for PHMs. Change of CDF should be permitted only if it is approved by State Pollution Control Board or Pollution Control Committee. Then at what point you need to once again recalibrate? After any major repair of the system, that is one. If it is a major repair, you need to recalibrate your system. Change of lamp for that particular type of particular system where you need to change the lamp. Readjustment of the alignment, sometimes the system is not aligned properly. If readjustment has been taken place, you need to report that. Change in fuel quality, the system shall be recalibrated against isokinetic sampling method. Once again, triplicate samples at each one. So these are the points which you have to keep it in mind, that merely changing them will not serve. You need to recalibrate your system, and then you have to report to the authorities also. It is advised to carry out PM emissions monitoring on the day when plant operates under capacity due to any reason besides the routine monitoring. As you said about the 3 points, so one point is once you are running it regularly. The other point you can take it when the plant is running due to any reasons, under capacity or probably under shutdown, whatever may be the reason, you can then perform the test just to see and ensure that the CDF, that dust factor what you have calculated, is more or less in the same path what you are looking for. Other requirement says the data capture rate of more than 85% shall be ensured. So if the data is coming, if you say no, my plant is not working or this is not working or the data is not being transferred, at least 85% criteria need to be taken care of. The data comparison, calibration, verification shall be done by laboratories empaneled by the CPCB using standard reference methods and at the frequency specified. Now although as on date no laboratories as such have been given this task, but the people who are NABL accredited, they are probably the ones. I think Sanjeevji, the people with NABL laboratory, they are performing this test, but whenever they are doing it, the other criteria, the requirement, need to be followed, which probably I have shown it to you. Wherever you get the point, see and ensure that the data is properly taken care by appropriate sampling method. So friends, if we really want to improve quality of air, see the basic objective of doing everything, see we should be thankful for pollution control boards that if they do not have restrictions of such a type thing, then probably nobody will do any type of control measurements. So if we really want to do, we need to control emissions, and the way it is done is regular, simple, accurate monitoring and calibration is the key to the pollution control. So thank you friends, and if you have any queries or questions, probably I know many of the things, probably the calculation part I purposely missed it, which probably I'll be covered up tomorrow once we go to the site. Once we do that sampling, by taking the real values, putting in the formulas and then calculating, you will have a very good feel of how that particular exercise has to be carried out. Now if there are any queries or the questions, probably I'll be too happy to answer. Yes sir.
The stack is 275 meters, we are measuring at
80 meters.
The dia at that place is almost 15 meters.
15 meters.
And my probe length should be almost 3/4, that's near about 12 meters.
Yes.
Landing a probe at that height
Is a big issue.
biggest issue.
Okay. See, these are all practical problems which all of you should be aware of. This is something where probably if you need to do the justice with that monitoring. See, you are spending so much for installing Cems. Why? Because there is no way out. Regulators will not leave you. But the sampling probes also, you need to make the provisions. Even in a monkey ladder, I know people who are putting a rope and taking up these particular things upstairs. Hindalco at Renupur, they have 8 stacks, and what they have done, they have taken 8 sampling systems and they have made those particular systems right permanently installed on stack itself. They don't carry it anywhere. They have been permanently installed on that particular platform. So this particular exercise you need to just work upon. And see, everything is difficult. See, I'm not saying it is very easy. It is difficult, but you should know what are the areas which are grey areas. Where are you actually going wrong? I'm not saying you try to avoid it. You should understand. Because see, whatever is the requirement, you need to do this particular exercise once. See it yourself. Whether does the monitoring at 8 points, 52 points making a difference. Suppose I am able to do the monitoring at 4 points and getting the constant profile. You are free to do that. But the basic principle, whatever is there, should be in your head. That yes, I need to do the sampling of 52 points. But you should be having a justification for some other changes which you have made as per your convenience. Nobody will listen to that. So you have made that as per your convenience, but then sometimes you have to practically think about the various problems which probably prevail at the sites, at the locations, which probably may not be convenient at all of the time. So this particular thing is quite possible. Any other question? Yes, sir. See, that's very right. Why do we need 3 points? Anybody? Yes. See, in order to check the linearity, suppose see you are making at 0, you are getting at 100%, at least you should have one more point somewhere in between. So that you are able to check this particular graph. It's a linear thing or not. And that's why they always say 3 point values. I think जब हम क्लास में स्कूल में थे they कहते थे कि आपको 2 लाइन बनानी है तो एटलीस्ट 2 points तो चाहिए. So the idea is that you are doing the monitoring so that the average what you will take, you are very close to that particular value. So that's why they always say 3 particular points. See, many things are practically very difficult. Even Cems installation was very difficult about few years back, but now with the technologies, with the expertise which is available, we are going towards it. So don't feel that it is very easy, but then it is not very difficult also. Whatever you do, try to first understand what is happening. What are the areas where we can go wrong? What are the areas I need to put special attention to? What are the areas which probably will make my things better? So think about it. And naturally there is always a scope of assuming many of the things, but then your assumption should always be closer to the real values. It should not be the other way around. Yes, sir. See, the particular chart I showed you in the beginning, there is a tabular form which says that 52 points basically means point, then I take a probe out, other point 13, then 13 and 13. So in a plane, that see 90 degrees apart will be at the right angle. You will not be able to cover up the whole of the cross section. So you need to have two portholes at diagonally opposite. In order to cover up the whole of stack, you need to have 4 portholes which are 90 degrees apart. 4 portholes 90 degrees apart, and then your particular length of the probe also. If you are doing only halfway through, and if it is 10 meters, you can manage the show with 5-meter probe set. See, in order to perform that test, you need to take those particular traverse points. See, there where it is the art of how you collect the sample. So once you do the sample tomorrow, probably then you can realize, once we be there on that instrument, how to set, where to put it on, when to put it off, then you can collect the sample. meter? Anybody? Okay. Now in your houses also you get dry gas meter for the measurement of consumption of LPG. Suppose it is not there, what will happen?
But sir, if you calculate the LPM, plus the because of that your time and velocity.
You are very right. Earlier, when the dry gas meter were not available, we are taking the values of particular rotor meter, say 25 liters per minute, then multiplied by the time is the total sampling period. But now dry gas meter is available, so then we should try to be more accurate and you know how much is the actual flow. So that gives you a better and more correct value. Anybody else? Yes, sir. Do we have time, Sanjeevji? Okay.
We are getting. But how we ensure that the dust factor that he has uh, set in the instrument, that is, it is accurate?
See, that is where the whole game is. See,
The manual, sir, manual monitoring sir हम कर रहे हैं. That is okay. Manual sampling we are doing, and we are comparing with the sales value also. We are getting 8 to 9% deviation. Okay, that is okay. But the dust factor which he has said, how we can ensure that it is correctly set?
suppose it is not correct,
Yeah.
what will happen?
So the deviation will be more.
है ना? So the idea is that whatever dust factor has been calculated, see the idea of showing you all this exercises, you should know how the things are being carried out. Don't think Cems as only a black box. No. It does not give any value of its own, I told you in the beginning. So whatever value you will feed into the system, that system will start giving you that value. So that dust factor, whatever has been fed, the supplier of Cems might have given it with their own experience or by taking some standard value. But since you are the person who is there in the field and you need to do the monitoring regularly for checking it also, you should know how it is being done. It's quite possible that many times Cems supplier will not be sharing that values with you.
Yeah.
Probably I don't know, but they can or probably may not be. But does not matter. What is more important is you should be able to see how that values you are getting on that screen of Cems is the same as what you are getting with the manual system. If that is falling in the range, it means whatever factor has been fed into the system is more or less alright. But you should know it. Any other queries? Thank you so much, and we'll be going there tomorrow for that field exercise. And I feel all of them are coming, sir. Okay. So we'll be sharing one data sheet also, and probably try to bring your own calculators also tomorrow. Thank you.
are generally calibrated with electronic input signal. So calibration error is the difference between the concentration indicated by the Cems and the known concentration generated by a calibration source when the entire Cems is challenged. The calibration error test is performed to document the accuracy and linearity of the Cems over the entire measurement range. So like I had mentioned earlier, in quite a few cases we use dual range instrumentation. So under normal controlled operation, that would be the low range of the instrument, or a low span. And then we would use a high range or high span for uncontrolled situations. So we do have to perform calibrations on each range. We have a calibration drift. The calibration drift is the difference of the Cems output readings from the established reference value after a stated period of operation during which no So typically in the United States, the calibration equipment is located on the ground. There are occasions when we do have stuff located up at the test platform, say maybe in situ or something like that. But generally speaking, we have an air-conditioned building that is maintained at a constant temperature, typically somewhere in the 70-degree range, Fahrenheit. The cylinders are mounted to the outside and they are fed through regulators. I can show you here in a minute. These are high quality, non-reactive materials are used for the transport of sample and calibration gases. This is quite important, whether it's some non-reactive metal tubing that's used as your sample line. In some cases we do use stainless steel as the sample transport, but most often we use like a Teflon or PTFE, depends on the application. Stainless steel or non-reactive materials are used for the calibration gas regulators. This is especially important with gases that are very reactive. You can have silica-coated wetted surfaces to help minimize corrosion. Typically with your normal gases, they're stainless steel or brass. Gases must be certified under EPA protocol gas, under the EPA protocol gas verification program. All calibration gases except for zero gas must have NIST traceability, which means it goes back to a known standard material. The EPA established the protocol gas verification program to ensure consistency and traceability for protocol gases. EPA protocol gases must be obtained from a manufacturer participating in the protocol gas verification program. So there's a running book with approved manufacturers. The EPA maintains a list of gas manufacturers participating in the PGVP on its website. Protocol gases must be prepared according to EPA document 600R12-531, dated May 2012, EPA traceability protocol for assay and certification of gaseous calibration standards. Gas vendors are subject to periodic blind audits and results are posted to the EPA's website. You can view these results at the following link. Pardon me? It's National Institute of Standards and TARS. I think that's, yeah. We just call it NIST. It is a clearinghouse where they look at source materials, source reference materials, and they come up with protocol calibration standards, traceable standards for just about everything. National Institute of Standards and Technology, yeah. Calibration gases can and often are combined or blended with compatible constituents that are non-reactive. So rather than having a single bottle of, say, SO2 and a separate bottle of NOx, for example, we would combine those to be able to show a calibration error through the entire range of the instrument by just using one bottle. So you don't have to have multiple valves and plumbing, excess plumbing. So you can kind of see in this picture, this is only half of one shelter that we have. And we have the regulators are mounted up top. On top of those regulators, we have pressure sensors, so we can monitor the pressure in the cylinders. So if one starts to run low, we know when it's running low. An alarm is triggered in our data logger, our data acquisition system. It will send an alarm to the control room, and they will know when they need to change out a cylinder, for example. Calibration blended gases are analyzed and certified according to PGBP. This technique allows for multiple calibrations while flowing gas from a single cylinder. Calibration gases are delivered through the entire system to the sample probe. In some cases, it has been discussed where you could have a valve up at the top to help speed that along, but in the United States you are not allowed to do that. You have to, the attempt for the calibration error is to send up the gas at normal conditions, so under normal sampling conditions as well. So the calibration gas is fed up to the sampling probe is flooded with the calibration gas, and it is drawn back through the system down to the analyzer as it would be under normal sampling conditions. Over and under pressurization can adversely affect your calibration results. So when you're looking at your sample flow through the system, you set up your calibration gases to flow very close to that, within 10% through a rotameter, and you can make sure that everything is getting a consistent reading. Clean and dry calibration tubing minimizes potential bias of the system, especially when calibrating with reactive gases such as SO2. So Roland mentioned this previously, so it is a good idea on an annual basis, or if you see material starting to build up or coalesce on the inside of your tubing, to probably look at cleaning it. You should do this probably, the company I work for, does this on an annual basis. They have their technicians go up to the stat test platform, or the platform where the probe is located, disconnect the lines, and rinse them with typically water or acetone, something along those lines, and collect that at the bottom and run it dry. It's important to make sure you run air through that dry air to make sure you clean out that moisture or any residue. That will cause a problem. Yeah, that's gonna, yeah. So, if you're wondering why your SO2 or NOx are being funny, so the daily calibration specification is the daily calibration using zero gas in either a mid or high calibration gas. There again, under normal conditions, if you are calibrating, you would use your low gas, or your mid gas would probably be in the expected concentration range. Your calibration error cannot exceed 5% of the span value, or 1% of CO2 or O2. If the calibration gets to 2.5% or 0.5% CO2 or O2, this is what we refer to as a maintenance limit. And this is something that's a useful tool. So if we have this set up with a special flag, so when we reach that point, operations or your technicians, whoever is maintaining your system, can go and address the system before you exceed the maintenance limit or the calibration error limit, and keep the system operating normally without having invalid data. Just because you reach 2.5% doesn't mean you're invalidating data. It just means you're going to go into a QA process of cleaning and maintenance and address the issue. Alternatively, if you're running on particularly low spans, if your NOx and SO2 are below or equal to a 50 ppm span, and the result does not exceed an absolute value of 5 ppm, or 10 ppm for spans between 50 and 200 ppm, then you are still within the acceptable range. If the daily calibration does not meet these criteria, then the system is considered out of control, and that data is invalid back to the previously good calibration. So you would be penalized back to the previous morning or afternoon, whenever you did your calibration. Flow monitoring systems cannot exceed 6% of the span value or 0.02 inches of water column. Your opacity monitor must not exceed 6% opacity difference on a daily basis. So calibrations are conducted in a hands-off manner. If you have an issue with after your calibration or as a result of your calibration, then you can complete the calibration and then you move forward with maintenance activities to try to address it. Calibrations are conducted within 8 hours of unit startup. This allows the unit to come up to load and become stable in operation. So you don't have, and also the Cems sampling system comes to equilibrium. That way you hopefully are under normal conditions at that point. Calibrations are controlled by the data acquisition and handling system. As indicated earlier, the data logger for us is what's controlling most calculations and also most input-output functions as far as triggering calibration valves and doing all of that. So our data loggers, typically in the US, are calibrated with sequence programming to activate a calibration when certain conditions occur. So if we put fire into a boiler, you can see when we're in startup, it'll be flagged with, say, an F, for example, for fire, and that will start the timer. And after an 8-hour period of time, as long as that clears and you're moving forward, then it will automatically go into the calibration sequence and trigger the valves as needed to send the gases. At that same time, those equations are looking for values that are within the acceptance criteria. Data logger can also be programmed to perform calibrations on a routine clock basis. If you're a normal base-loaded unit and you're running 24/7, then you can have it set to where it's running at a particular time each day. If the parameters are exceeded, the data logger will flag the data appropriately, which provides an alarm for the parameters. That alarm is also sent to the control room. So at that point, then the control room is aware that they have an issue and they either need to bring the unit offline or put the unit into some sort of position where they can move forward with corrective maintenance without jeopardizing, or I should say minimizing, data loss. If the calibration fails, then the unit is considered out of control and maintenance is performed as soon as possible to minimize the invalid data period. Once corrective actions have been completed, a hands-off calibration must be performed to return to normal operation and have valid data. In some cases where instrument repairs include the replacement of critical parts or the sampling system, such as a dilution orifice, certain QA procedures need to be performed in addition to a calibration, such as a linearity, or depending on the severity of the situation, it could be a full linearity or it could just be one pass of the 3 gases to show that you have maintained linearity. So this is an example of a chart that we use within our stations to track what happens if this happens. So if you change your entire Cems from a dilution Cems to an in situ Cems, you have to do all of the certification procedures. If you replace or repair signal wiring in the Cems shelter, you just have to do a calibration. because the instruments themselves weren't necessarily touched or modified. If you replace or repair a vacuum pump or pressure pump, not in the analyzer, there again you only have a calibration. So this is a good baseline for how to assess the impact of maintenance and service that has to be performed on your system, and what actions need to be done to continue to keep the system in certified and valid operating condition. So calibrations are important. You know, calibrations are not just a formality. Your calibration should be looked at as a useful tool. You can use it to troubleshoot your sampling system. You can troubleshoot the instrument itself. You can look at your conditioner. There are several things that you can do if you know how to look at it, because you're assessing the entire system on a certain frequency. You can predict trends in performance. You can start to see excessive drift. You can tell if you're using a chemiluminescent analyzer, for example, for NOx, you can start to see when the photomultiplier tube is starting to decay. I mean, there are some good things there. Routine maintenance is essential. If you have to use a annual maintenance agreement with your vendor, then I suggest you do that. It is a good idea to have somebody on top of everything at all the time, because you don't want to be chasing the issue later. The problem could be very subtle and difficult to locate, or it could be something far worse. Like I suggested previously, if you have material buildup, you can get salts that build up in your sample lines. You can get excess particulate. You may think that your filter for your extractive Cems is seated properly, and you could get very, very fine particulate breaking through there and getting into your line. That can cause SO2 to scrub. It can cause interference with some NOx. The environment these systems operate in is hostile. Do not underestimate the corrosive nature of what happens to your sample probe, the liner, everything else that's involved. You can watch the Teflon tube start to yellow and age and get brittle, or get dry. And you can have pinholing in your probes. You'd be surprised what a little bit of corrosion can do to your system. And you would never even necessarily realize it was there. You look down the probe, you're looking at everything, you're like, oh, everything's fine, I don't know where the leak is coming from. You pull the sheath out, and the internal sheath, and you look at it very closely, and you can have a pinprick of a hole in there, and that will ruin your day and your data. So do not underestimate a calibration in a value. Even calibration system components fail. The tubing ages. Regulator wetted surfaces corrode. There are sintered filters in your regulators. They get gummy, especially with high concentration of acidic gases. If you're using 3,000 ppm gases for SO2 or very high, you will get material buildup, corrosion, and you do need to make sure that your regulators are maintained and rebuilt occasionally. Compression fittings leak. Every time you take one off and you tighten it back up, if you tighten it up a little bit too much, those ferrules bite into the Teflon line, for example. And over time, they will develop cracks, and if there's any sort of weight or pressure on that Teflon line, it will cause that line to eventually just split. Now, as soon as you get enough in there, depending on what it is, where it is in your system, you could potentially start pushing or sucking in ambient air, or you could be pushing calibration gas out there and not getting it up to the probe the way it's meant to be. You can also have a whole myriad of other failures, such as heated lines. Heated line, the heater core can fail. If that fails, you get condensation in there. You're going to have scrubbing. Pump heads get leaks. The membranes, the Teflon liner for the head cracks. These things age. Peristaltic tubing commonly used in your chiller, for example, to help evacuate the water out from the impingers. You need to replace that with some frequency. It gets dry, brittle, it'll fail. And especially where it's being rotated against the rollers on the peristaltic pump, that eventually will crush and cause leaking. All right, so anybody have any questions on calibrations, equipment? Any questions at all?
In India we are using calibrated gas cylinders. It has a, we call it a stability period. It has a stability period generally of 12 months. What is stability period for the gas in the cylinders?
Right, so the usage period for, or stability period for the gases in the United States varies depending on what makes up the gas. So if you have, for example, NO2, nitric dioxide, if you use this, sometimes we use this for a converter check in the United States. Anyway, if that is a very reactive gas, so you would have a very short period of time you could use that gas, say 6 months. However, for your normal calibration gases, like we'll just say a 200 ppm NOx and a 500 ppm SO2, that is actually good for probably 8 years.
8 years?
Yes.
So for a 3000 we are using it's 12 months a year.
So in the United States, under the Protocol Gas Verification Program, the manufacturers of the gas are using special materials like aluminum, or they're blending these gases. They're using stabilizers. They've come a long way with their technology as far as being able to maintain or produce a stable gas, and that has shown over time, so that they can be used for quite a while. So back in, I think it was 2018 or somewhere around there, they extended them out to like 8 years from a 3-year period.
If we are using it after 12 months, my results, what happened to those results?
So if you were to use a gas after
its stability period.
if it's expired,
Yes.
right? You can have it recertified, right? You can send it back and have it recertified and change out the gas, and then if the recertification comes back and it's within the acceptable tolerance of the original concentration, then you could be okay.
So, what is a cycle test with gas calibration? Cycle test.
The cycle time test?
Yeah.
That is, the cycle time test is for you to understand the response time for the analyzer through the entire system. So the gas is sent up. Well, you first start with extracting stat gas, and then you will run a zero gas up there, and you measure the 95% step change. So you do that up and back. So what you're doing is you're trying to quantify the amount of time it takes for the sample to travel to your instrument through all the plumbing, and you get a valid reading, or a stable reading, I should say.
Thank you. Regarding mercury analyzer, can you please say something? Why it is difficult to analyze?
He's gonna go through that.
Oh,
Yeah.
Thank you. Thanks.
No
I
problem.
overstepped.
Oh, that's okay. It's all right. The,
gases using the low from low to medium to high, or so what will be the gas concentration passes, sir?
The percentages of of the
Yeah,
concentrations.
yeah, yeah. Sequence, yeah. That is, it will be low, medium, high, or
You want the sequence?
yeah, sequence.
Okay, so the EPA does not want you to duplicate injections. So you can start largely in any sequence you want, right? You could go high, mid, low, high, mid, low, high, mid, low. You cannot go high, mid, low, low, mid, high, right? And then high, mid, low, because they don't want you to follow one gas with the exact same gas, right? Or duplicate injections right after each other. So the expectation is you're going to go in order for each of the three injections. Does that make sense?
Sir, what is PGVP? PGVP.
What's that?
Calibration blended gases are analyzed and certified according to PGVP in one of the slide associated with the calibration gases.
Right.
PGVP.
The Protocol Gas Verification Program. That's what that stands for. So your questions regarding offline calibrations? So we're so under Part 75, which is largely what I've been speaking to, we are required to conduct all calibrations while the unit is combusting fuel. It does not necessarily have to be generating power, but there has to be a fire in the boiler, and you want it to be somewhat normal requirement. You can do a calibration or perform a calibration when you are offline, right? However, under Part 75, if you are a subject unit, you have to do a offline calibration certification, which is really nothing more than just because if you're using an extractive dilution type Cems, it can be, you really want it to be at equilibrium with the stack conditions, because you can get some variability there with the orifice and some other things that if they're cold. So, however, if you are a peaking unit like a gas turbine, we typically use straight extractive, and those aren't necessarily as subject or prone to having issues associated with being at equilibrium within the stack. So you can do an offline calibration for that, which is great because then when you go to start the unit up, you don't necessarily have to wait for your calibration. You can do it previously, but really, online calibrations are what we normally do. Anyone else? The stack conditions, because you can get some variability there with the orifice and some other things if they're cold. So, however, if you are a peaking unit like a gas turbine, we typically use straight extractive, and those aren't necessarily as subject or prone to having issues associated with being at equilibrium within the stack. So you can do an offline calibration for that, which is great because then when you go to start the unit up, you don't necessarily have to wait for your calibration. You can do it previously, but really, online calibrations are what we normally do. variability there with, or if there's things you can smell if they're cold. So, however, if you are a peaking unit like a gas turbine,
Hello.
Once you get into the page 1, it will
you're,
be
you
connected to
typically
another document
use
which is
straight
another thing.
extractive, and those aren't necessarily
So
gas
it
cells,
goes
but
around and
prone
round. So
to
I
having
put up
issues
to
associated with being at equilibrium within the stack.
related to that,
So
but it
you
is
can do an
more
offline
complete.
calibration for that, which is great, because then
specific
when you go to start the unit up,
the
you don't
requirement.
necessarily have to wait for your
Say,
calibration.
Pullman,
You can
or
just
not,
previously
what
do
is it? So both are
Really
interconnected.
online
So
calibration.
part 5 is continuous emission monitoring requirements, all the details of US Code of Federal Regulation. Right?
Anyone else?
Thank you.
The stack conditions, because you can get some variability there with,
Okay.
or if there's things
Now
you can
comes
smell
the real fun
if they're
part.
cold. So, however,
Something
if
we were
you are a peaking
looking
unit
for
like a gas turbine,
since time, and
Hello.
something what is new.
Once you get into the page 1, it will
you're
be connected to
typically
another document which is
straight
another thing.
extractive, and
In
those aren't
Cems,
So
necessarily
it
gas
goes
cells,
around and
but
round. So
Mercury,
I
what
having
was
issues
it all about?
associated
Why
with
should
being
we
at
do any
equilibrium
mercury?
within the
Oh,
stack.
related to that,
So
but
you
it
can
is
do an
more
offline
complete.
calibration for that, which is great, because then
specific
when you go to start the unit up,
the
you don't
requirement.
necessarily have to wait for your
Say,
calibration.
Pullman,
You can
or
just
not.
This
What
is where we are looking. Let's
So
just
both
say
are
monitoring
interconnected.
total.
online
So
calibration.
part 5 is continuous emission monitoring
Mercury.
requirements, all the
What
details
is it?
of
It's
US
the
Code of
only
Federal
metal
Regulation.
which is
Right?
Anyone else?
present in liquid form at ambient
The
conditions.
stack conditions, because you can
We
get
have,
some variability there with,
Okay.
or if there's things
Only
you
heavy
can
metal.
smell if they're cold. So,
Atomic number is 80.
However,
Something
if
we were
you are a peaking
looking
unit like
for
a gas
since
turbine,
since time, and
Hello.
something that is new.
Once you get into the page 1, it will be connected to another document which is another thing.
In Cems,
So it goes around and round. So what
having
was
issues
it all about?
associated with.
why
You
should
see
we do
heavy
mercury?
specific
Oh,
weight.
know that,
So
but
you
it
can
didn't.
do
Now
an
comes
offline
the
calibration for
important
that,
part.
which is great, because then when you go to start the unit up, you don't
Saturation concentration at 0 centigrade,
Or not.
15 milligrams per cubic meter. Let's
So
just
both
say
are
relatively
interconnected.
high
So part
concentration,
5 is
which
continuous
can be
emission
present
monitoring
at
requirement,
0
all the
centigrade. What is
details
it?
of
The highest
US
temperature goes
Code of
only
Federal
metal,
Regulation.
with the saturation
Anyone else?
concentration in liquid form. Elemental mercury is not water soluble.
because you can
We
get
have
some variability there
zero.
with,
Okay.
It's compound heavy metal, mercury 1, atomic mercury 2
however,
salts.
if
They
you are
are
a peaking
more
unit like a
For
gas turbine,
since time, and
Hello.
something that is new.
minus
It
and
will be
can
connected to another
be
document.
solved
straight
with
extractive,
In
and those aren't
Cems,
necessarily
So it goes around
We
and
heard
round.
that.
So
Yes, the
having
was
issues
about.
associated with.
You see heavy weight specific weight of GE. Now comes important takes out
Great,
mercury.
because then when you go to start
Takes
the
out
unit up,
saturation concentration from 0 centigrade, 15 milligrams per cubic meter. Let's just say relatively high
So
concentration.
part 5
Why
is
is it
continuous
important?
emission monitoring requirement, all the
What is
details
it?
of US
Temperature goes
Code of
only
Federal
metal.
Regulation.
It is very toxic, present in liquid form. The mercury is the bad thing of mercury here is
Okay.
it's compound heavy metal. If I breathe in mercury, salts, a high concentration of mercury,
since time, and
Hello.
something that is new.
feel anything.
It
And
will be
no
connected to another
denying
document.
In
poison
Cems,
my
Goes
body.
around
We
and
heard
round.
that more.
Right,
Yes,
I-
our bodies, as any heavy weight specific weight of GE, now comes important takes out
Great,
and
because then
organic takes out saturation concentration from 0 centigrade, 15 milligrams per cubic meter. Let's just say their
So part
bioaccumulation.
5
Why
is
is it
continuous
when we
emission
breathe in?
monitoring requirement, all the
What is
details
it?
of US
Temperature goes
Code
only
of
metal.
Federal Regulation.
It is very toxic, distributed liquid form. The mercury is the bad thing of mercury totally is it's compound. Total mercury by freeze in summary signal element high all forms of mercury.
Hello.
So right new mercury sulfate and I carry the side poison.
Goes around
we heard that more. Where is he? Have you heard takes all hands organic bodies of acceleration organic codes specifically the so-called US, which were always it is very important to illustrate the shoreline with a lot of lowest point total is not far so that the size of the summary system we should not forget Wait, you should not forget word of which we wanted to work in Wait, you should not forget word of which we wanted to work Wait, you should not forget word of which we wanted to Wait, you should not forget word of The nice
Thank you.
Thank you. At that time, by the way, when the instrument was then developed and worked and
It is necessary to
installed
sample
and everything
as
fine, we were talking about two At that time, by the way, when the instrument was then developed and worked, industrialized, and installed, and everything fine, therefore we were talking about work in
I have one more question.
At that time, by by the way, it is not when the instrument was then developed and is industrialized and installed. Heritage are there for we were talking about work. You might in my time, by the way, it is not when the instrument was then developed and is industrialized and installed. Heritage are there for we were talking about work. You might in my time, by the way, it is not when the instrument was then developed and is industrialized and installed. Heritage are there for we were talking about work. You might in my time, by the way, it is not when the instrument was then developed and is industrialized and installed.
Hello.
Heritage are there
Recently, we
for
have
we were
talked
talking about work. You might in my time, by the way, it is not when the instrument was then developed and is industrialized and installed.
Hello.
Heritage are there
Recently,
for
we
we
have
were
talked
talking about work. You might in my time, by the way, it is not when the instrument was then developed and is industrialized and installed.
Hello.
Heritage are there
Recently, we have talked
you might
Okay.
Hello.
Recently,
Hello.